Yeah. Perfect. Okay. So this is the last distribution of chapter 4 that we cover, exponential distribution. You know, the midterm will not cover chapter 4, but I think understanding the material from chapter 4 will definitely help you in the midterm, because we are still, you know, working with probabilities, conditional probabilities. So I do encourage you to, you know, study chapter 4 as well, because I think it will help you better understand the previous chapters. So basically, in the last class, we didn't really solve this example. I just quickly mentioned what the answer is. So we have a large corporate computer network. So I forgot to ask, so people over Zoom, anytime that you have a question, you can go ahead and ask your question, unmute yourself and ask a question. So user logins to the system can be modeled as a Poisson process with a mean of 25 logins per hour, right? So we want to highlight this. What is the probability that there are no logins in the next 6 minutes, right? So the question says the number of logins is a Poisson process, and that means that the distance between the logins is exponential, right? So that's always the case. If some process is Poisson, then the distance between the events in time or in meters or whatever, it's exponential, right? And remember that a PDF of exponential was f of x is equal to, I think it was lambda e to the minus lambda x, right? So, so basically, we want to calculate the probability that there is no logins in the next 6 minutes, right? So this is the PDF of an exponential, right? And the integral under this thing from 0 to infinity is 1, right? And that means that when something is modeled as a Poisson distribution, then the distance between the two events can be, you know, like a very small time or a large time, or, you know, some distance. But it means that, you know, the next event is going to happen sometime, right? We don't know when, but it's going to happen, right? So because of that, the integral under this curve is 1, because we know it's going to happen, the next login to the system, right? So we want to calculate the probability that there's no login in the next 6 minutes. And that means that we have to calculate the probability that the time is actually more than, so 6 minutes equals to 0.1. So you have to always decide what is your unit, right? So in this example, we decided on a unit of minutes, right? Sorry, hours. So because we decided that 25 logins per hour is our lambda. So lambda is 25. And it's per hour, right? Because our unit is hour, then we have to convert this 6 minutes into hour. That's 0.1 hours. And so it's good to calculate the integral of exponential. You see that it's an easy function. So integral of lambda e to the minus lambda x from a to b is going to be equal to, so exponential is exponential, the integral of exponential. So that's going to be minus e to the minus lambda x from a to b, right? Yeah, everything looks good. So this is going to be e to the minus lambda a minus e to the minus lambda b, right? So that's the integral of exponential function from basically a to b, right? So basically, this area under the curve is this number, right? So we can quickly check if this is correct. Any suggestions how we can check this? How do we check if we didn't make a mistake? So what numbers do I plug in for A and B to quickly check? Exactly. What's your name? Say it again. Zavi. Yeah. So yeah, I hope you don't mind me saying your name. It's okay. All right. So yeah, so I mean, a very good pair of numbers to plug in for A and B would be 0 and infinity, right? And if you do that, you will see that this is integral of minus infinity, that's 0, and in e to the power 0 is 1, so it is 1. So I think we didn't make a mistake, it's okay. So, and the integral from 0 to infinity should be 1, so that's okay. Is it clear? Okay, so now let's plug in the numbers in the bound that we have. So in the bound, we have 0.1 for A and infinity for B. So infinity for B, it means that this guy is 0. And basically, we have to put e to the minus lambda times 0.1. So that's e to the minus 25 times 0.1, right? So that's why you don't see another term minus something here, because it's e to the infinity and that's 0. So the probability is 0.08. Right, so this area under the curve is 0.08. So there's 8% chance.
But is it always negative like that? Like, the question is no log on to the next 6 minutes. So if you want to find will.
Yeah.
So how do you know like that?
Yeah, that's a good question. So we can in fact do that one, like right here. There's some white space here. So, or perhaps we can open a new page. I don't think there's. Oh, actually, yeah. Just close and open. We have a lot of empty space. So just the only thing that we still need is the fact that integral of lambda e to the minus lambda x from A to B is e to the minus lambda A minus e to the minus lambda B, right? So let's just keep this. So now the next question is, what is the probability of having a login in the next 6 minutes, right? So let's say this is the question now. What's the probability of having a login in the next 6 minutes, right? So now what I have to do is I have to calculate basically the probability of this curve from 0 to 0.1, right? So that is going to be integral of f of x d of x, and then my bounds are from 0 to 0.1, and then so I already calculated that, so that is going to be e to the minus lambda times 0 minus e to the minus lambda times 0.1, right? So e to the power 0 is 1 minus, and this guy is e to the minus 2.5, and this is 1 minus 0.082, right? Which is probably like 0.918. Thank you. Yeah. Oh, very good question. So this is the probability that there's exactly one login in the next 6 minutes. Because if there's multiple logins, then exponential is only distance between two logins. It doesn't deal with multiple logins. It's always two logins. So, or in this case, until the next login, right? Any other questions? So there is one more way to solve this question. So you saw that basically like one solution to this question was this guy here. One solution was to calculate the probability that there is a log in here and then subtract one from this, right? Calculate the complement, right? And then there's a third solution, which is based on the Poisson distribution. If you don't understand this one, it's okay, because you can use the exponential distribution, because this one is a little bit tricky, right, conceptually, right? So I'm going to solve this question, but use Poisson distribution, not use exponential, right? And let's see how we do that. So I say that, okay, I want to calculate the probability that there's no login in the next 6 minutes, right? So in fact, actually, it's not difficult, right? So we have done this before, right? So I have a Poisson distribution. I want to calculate the probability that there's no login in the next 6 minutes, right? So all I have to do is that I have to convert this 25 to 6 minutes, right? So basically, I have my lambda, my new lambda is going to be, so 25 logins per hour, and that means 2.5 logins per 6 minutes, right? So lambda is 2.5 per 6 minutes, right? So now I have a Poisson distribution where the average number of logins is 2.5, and I want to calculate x equal to 0, p of x equal to 0, right? And we know how to do that. So here, I'm going to calculate probability that the number of events in the Poisson distribution is 0, right? And now I'm going to plug in. So remember, the Poisson distribution was e to the minus lambda divided by x factor lambda to the power. So what is the equation? I don't remember actually. Is this correct? Is correct what I wrote? Okay, thank you. Oh, it's positive lambda to the power positive x? Okay, thank you. So lambda to the power x, e to the minus lambda divided by x factorial, right? So I just plug in 0 for x. So this will be e to the minus 2.5 times lambda to the power x, and that means lambda to the power 0 divided by 0 factorial, right? And that's e to the minus 2.5. It's the same answer. Okay. Sorry about the noise. So yeah, I take that back actually, that this one is a little bit tricky. I don't think it's tricky, right? So I just used basically chapter 3 material, right? I said that I have 2.5 logins per 6 minutes. I want to calculate the probability that there's no logins in the next 6 minutes. So my x is equal to 0 for the Poisson distribution. Any questions? Okay. Oh, so if there's a question, I see that there's something in the chat. So let me try to see that this time. But if there's a question, just unmute yourself and ask the question, because it's I have to quit presenting. So do you want to read out the question, or you think it's okay?
Yeah, sure. I'll read it. I'm wondering how come it's not p of x less than or equal to 0.1.
So what is this? Sorry. Oh, here you mean that why we are calculating probability of x more than 0.1?
Yes, because like on the right we did the version of chapter 3. Yeah. But I was wondering how come we didn't do p of x less than or equal to 0.1 instead of p of x equal to 0.
Oh, for Poisson?
Yes.
Oh, for Poisson, because the question says there should be no login in the next 6 minutes. So no login means that 0 login. So X should be 0. It's not less than or equal to 0. It's exactly 0.
Okay, sorry, I didn't see that. Thank you.
Yeah, sure. Other questions? Okay. And you shouldn't be sorry. I always encourage questions. If you have questions, I'm sure you know it's not clear to other students as well. So no question is a dumb question. Yeah.
How can we solve the probability for one login in the next 6 minutes with the distribution formula?
Yeah, we can do that. So basically what we have to do is, remember first we converted lambda is 2.5, right? And then I say what's the probability that X equal to 1, right? So that will be e to the minus lambda, lambda to the power X, X factorial. And here I plug in X equal to 1. So that gives me the probability that I have 1 login in the next 6 minutes. Is that the question? Yeah. Did I answer the question or yeah? Yeah, so here, I mean, yeah, of course, this will be a different number. So, right, so this will be, so here, this will be e to the minus 2.5 times lambda times 2.5 divided by 1, right? So, of course, this number is not the same number here. Yeah, of course. I mean, this is a new thing that we calculated. So here, it's completely a new question. Here, I calculated the probability that I have 1 login. Oh, so now I get the question. Okay, so you're saying that f of x equal to 1 should be equal to, here I think I got, so p of x less than 0.1. We calculated it. It was integral from 0 to 0.1 of f of x d of x, right? And this was 0.91, no, sorry, 0.17, I guess.
Yeah,
18, right? So this was the number that we got, right? And now probability of, yeah, that's an excellent question. So if you calculate this number, this is 2.5 times this. So this is around, this is 0.8. So this is around 0.3, I guess, right? What is this? So this is, so I will write here, 0.205. Yeah, that's right. Now the question is, yeah, so this is definitely beyond the scope of this course, but we can try to answer it, right? So the question is, these two are not equal. Any ideas why? So it's a question that one of you asked before. What was your name? Zavi, yeah. So it relates to the question that you asked before.
So it's for the probability of having exactly 1 login versus the probability that it takes less than 6 minutes to have 1 login.
Yeah, but these two are not equal. Why is that? Yeah, they are not the same thing, but how can we make this to be equal to this? Obviously, we should add more to this, right? It's obviously smaller, right? So what are we missing here? Yeah. Yeah, exactly. That's what we should calculate. So here, we shouldn't calculate just x equal to 0. We should calculate probability of x more than or equal to 1. Sorry, we shouldn't calculate f of x equal to 1. We should calculate f of x more than or equal to 1, right? Why is that? Because if in the next 6 minutes, we have 2 logins, then again, this condition is satisfied, right? We have 1 login in the next 6 minutes, right? So we are only calculating part of the probability here, right? I'm only calculating the probability that I have exactly 1 login in the next 6 minutes, right? But if I have 2 logins in the next 6 minutes, this condition is again satisfied, right? The distance between them is still less than 0.1. If I have 3 logins, the distance between them is less than 0.1, right? So I have to add all of those guys. And once you add them, you get the same number. Yeah, so basically, okay, so this is, so basically here, what I have to do is f of, so here I'm talking about this f, right? So I mean, my notations are a bit, it's not a good practice because I call both of them f, right? Exponential is I call f, Poisson I also call f, right? But let's distinguish them, right? So let's call the Poisson distribution f of p and exponential distribution f of e. So here I was referring to exponential distribution where I wrote f, and here I was referring to the Poisson distribution, right? So f of p, sorry, f of p for x more than or equal to 1 is going to be p of x less than 1, right? So here my x is the Poisson x, and here my x is the exponential x, right? So here, to make this equal to this, I have to add f of x equal to 2, f of x equal to 3, f of x equal to 4, an infinite sum, basically. And then that becomes the same as, so here, my x is the exponential x, right? Exponential x, because this x is the distance between events. This x is the number of events. They are different x's, right? Yeah.
So we just did use the discrete Poisson distribution to find the number of the probability of no log ones in 6 minutes, right? So we can just subtract that from 1.
Exactly. Yeah, that's a great idea. So instead of calculating this, I can write down that this is equal to 1 minus f of Poisson, x of Poisson is equal to 0. That's an easier way, right? Instead of doing an infinite sum, I can say that is equal to the complement, right? Yeah, so great discussion. But don't worry if this didn't make sense, because I think it's a little bit beyond the scope of this course. You can watch the video later if this doesn't make sense, and I will be happy to do it again next week. Any questions? Yeah.
Will the answer be same if we write x of Poisson greater than 0 instead of 1, greater than or equal to 1, we just write greater than 0.
Yeah, we can do that. Yeah, that's okay. Yeah, so here we can, so this is, oops. So this is also equal to f of x of Poisson more than 0, right? Because x of Poisson is an integer, is a discrete number, right? So if it's more than 0, the first number it can take is actually 1. Any other questions? Yeah.
Just to make sure I understand. So the x in the exponential function represents time, but the discrete one it represents a number.
Exactly. Yeah. Yeah. So x in the exponential distribution in this case, so I denoted as x of e, that is time between logins, and x here is the number of events, right? So they are completely different, right? So like here is time, but like in another case, if we are looking at, for example, like cracks in a wire, right? So here x is the number of cracks, this x is the distance between the cracks. Okay, so don't always try to use Poisson when the question is asking for like between time, because sometimes it becomes tricky, right? So in fact, in the next, yeah, go ahead.
Yeah, I think you're probably going to answer my question.
Yeah, okay, all right. So so let's look at this one, right? So what is the probability that the time until the next login is between 2 and 3 minutes, right? So the question is clearly asking that I want my login to be between 2 and 3 minutes. So it's clearly more straightforward to use the exponential distribution, right? So we just plug into that, for A and B, I plug in, 2 and 3 minutes. So this is 2 minutes converted to hours, and this is 3 minutes converted to hours. Right.
Yeah, so if you want to use Poisson for that, or any other interval of time, you have to like change your potential. Because you can always like.
Yeah, I think what you have to do here, we can try. I'm not sure if what I'm going to do is correct, but let's try. So basically between 2 and 3 minutes, right? So that means that I want to have a login in basically like in 1 minute, right? So the first thing I have to do is that I have to convert my lambda to minutes. So my lambda will be, 25 over 60, right? And now what I have to do is I have to say, so my f of Poisson for x of Poisson is equal to lambda to the power x e to the minus lambda divided by x factorial, right? So my lambda is this lambda here. Now I have to plug in.
So it would be 1.
Yeah, so I guess what I have to do now is that I have to calculate 1 minus f of x Poisson is equal to 0. That will be the same answer as this guy. Right? Because what I did here is that I said I will not have any login in 1 minute, and that's equal to this probability, because the question wants the login, some login to happen between 2 and 3 minutes, right? So let's calculate it actually. Can somebody plug this into a calculator? I'm curious to see if I made a mistake or not. So my lambda is 25 divided by 60, and then this is our x of Poisson, right? So basically what I want to calculate is the following: lambda to the power 0. Actually, that's not too bad. I guess we can calculate it. E to the minus lambda divided by 0 factorial. So that lambda to power 0 is 1, 0 factorial is 1. So all we need to calculate is e to the power minus lambda, where lambda is this guy, 25 divided by 60. What is this? 659?
Yeah, but you didn't do 1 minus. It's 0.34, so it's exactly double. Weird.
Yeah, I don't know. I have to think. This is a hard question.
Yeah, I think so.
Yeah, I can think about it and get back to you. But this seems okay what I did, right? So I converted it to per minute.
So maybe the difference is that like there's no logons before 2 minutes.
That's not all we want, right? We want one to happen. So we need to multiply this by the probability that there is one.
Yeah, but so basically this was the probability that there's no login in the between 2 and 3 minutes, right? 0.65. I have to think about it. So let's not waste classes time. Okay. So in the next part, what is the interval of time such that the probability that no login occurs during the interval is 0.9, right? So this question is the other way around. Instead of giving us the interval, is telling us what is the interval such that the probability is 0.9, right? So it's usually good to try to draw what's going on, right? So I want to calculate some x such that this area under the curve is 0.9, right? So my question is, what is x? Right. So remember, we already calculated this integral. So integral of lambda e to the minus lambda x from a to b was e to the minus lambda a minus e to the minus lambda b, right? So that means that integral from 0 oh, I think I made a mistake again. Yeah, so the question is saying no logging, right? So so basically what I calculated here, what I said here, 0.9, this means that I want a login to happen, right? That's exactly the complement of what the question asked, right? So the question is saying, what's the probability that no login occurs in this interval is 0.9. So this means that this guy is actually 0.9, right? So sorry about that. Right, so this guy is 0.9, and I want to find X. So basically now my bounds are going to be, so A is going to be X and B is going to be infinity, right? Because my bound is from X all the way to infinity, right? So integral from X to infinity of lambda e to the minus lambda X, d of X is going to be e to the minus lambda X, right? Because the other one is 0, right? This term will be 0. So that's what you see here. E to the minus lambda X is e to the minus lambda X. So here you don't actually see how the integral was calculated. This is how it was calculated. So how do we solve this equation? X is in the exponent, so all we do is we take the log of the both sides, and then we can simply calculate X after that. So X is 0.25 minutes. Any questions? Yeah, so somewhere in the back of my mind, I'm still thinking why. So I'm going to make more mistakes because I'm still thinking about why that was different. So the next question is, what is the mean and standard deviation of the next time until the next logging? So here we can simply use the equation in the crib sheet, right? Yeah, go ahead. Yeah, that's a very good question. That's the exact same mistake that I made, right? So let me explain that again. So this is the PDF of exponential curve, right? And I want to calculate the interval of time such that the probability that no login happens during this interval is 0.9, right? So you are right, actually, my interval is from 0 to X, right? So I want to calculate some interval such that the probability of no interval in this area is 0.9, right? But if I simply, so my mistake was that I simply said, oh, this is equal. So that means that this is equal to 0.9, right? That's not the case, because the question is saying no login in the next X minutes, right? So since I want there to be no login here, it means that my login has happened after X, right? So that's why the complement is 0.9, right? Or another way we can do this is that we can say that, okay, I want there to be no login in the interval. I want the probability that no login for X between, so here I have to write capital X, right? X between 0 and X, that is equal to 1 minus probability of login for X between 0 and X. right? So I want the probability of no login to be 0.9. And that means that this guy is 0.1. So this area is actually 0.1, right? And now I can, instead of the way we solved it here, I can solve this equation, integral from 0 to x of e to the minus lambda x, e of x, and there's also a lambda here. That is equal to 0.1. And it should give you the same answer as before. So here, I could solve it like this as well. Other questions? Okay, so here to find the mean, we have to use the crib sheet, right? So the question says that we have 25 logins per hour, right? So that means that in average, it takes around 2.4 minutes until the next login happens, right? And that does make sense, right? So we have around every 2 minutes, we have a login, and that's the same number here, right? So this number, 25 logins per hour, it means that around every 2 minutes, we have one login, right? And the average that we find is also around 2 minutes. And the standard deviation is 1 over lambda for the exponential distribution. Any questions? So that's it for this chapter, I believe. Oh yeah, there's one more thing that's actually not part of the, not part of the syllabus, but I think we can look at this as an exercise, right? So this, I mean, we're not going to ask you lack of memory property in the exam, but we can look at it as an exercise and try to solve this example, right? So the exercise is the following. What is the probability that x is less than t1 plus t2? So x is less than t1 plus t2. So we are somewhere here. Given that x is already more than t1, right? So I know that I'm already more than t1. So that means that what's the probability that I'm here? And that probability is equal to P of x less than T2, right? And T2 is the distance between these two guys, right? So before seeing why we call this lack of property, let's try to explain both sides of this equation, right? So first of all, remember that P of A given B is P of A intersection B divided by P of B, right? So that means that now the left side of this equation is equal to the intersection of these two, right? So what is the intersection of these two? I want x to be less than this and also more than this, right? So this is the intersection in the middle, right? So that is going to be P of x more than T1, but less than T1 plus T2 divided by P of B. So my B is P of x more than T1, right? So I just use the definition of conditional probability. Any questions so far? So for the exponential distribution, we can calculate all of these, right? So for example, in this case, the numerator is going to be integral of lambda e to the minus lambda x d of x from T1 to T1 plus T2. And then this guy is going to be integral of lambda e to the minus lambda x dx from T1 to infinity, right? So this is, simple arithmetic from now on. We can just plug in and calculate the left-hand side. Similarly, we can calculate the right-hand side. So P of x less than T2 is equal to integral from 0 to T2 of lambda e to the minus lambda x d of x. Right. So I do encourage all of you, this is not part of the course, but this part is part of the course, right? We apply, I mean, we didn't use anything fancy, anything new, right? We use this definition from previous chapters and we plugged in. So I do encourage you to like solve the left-hand side and also solve the right-hand side. And then you will see terms cancel out and these two are actually equal, right? So that is definitely not out of the scope of this course. You can definitely show that these two sides are equal. It's very easy to show. Yeah, yeah. Yeah, so we can definitely, we can write the left-hand side and right-hand side as A, B, C, and D, right? So here, this is my left-hand side of the equation. Sorry. Right? So I calculated the left-hand side all the way to here. And then if I want to write it in terms of A, B, and C, so the integral from T1 to T1 plus T2, that's C. And the integral from T1 to infinity, that is C plus D, right? And then this integral, so this is the right-hand side. So the right-hand side of this equation is equal to integral less than T2. So less than T2 is going to be A, right? So this is A, right? So as I said, if you do these integrals, you will see that A is equal to C divided by C plus D, right? This is definitely in the scope of this course. And I do encourage all of you to do this. It's super easy. But the part that is out of the scope of this course is the explanation and the meaning of that, right? So what is the meaning of this equation? I think it becomes more clear with an example, right? Instead of talking about T1 and T2, let's look at an example and see what it means. Right? So let X denote the time between detection of a particle with a Geiger counter. Assume that X has an exponential distribution with lambda equal to, or actually with expected value equal to 1.4. So remember, this is 1 over lambda, right? What is the probability that the particle is detected in the next 30 seconds? Right? So again, this is my exponential distribution f of x. And this is 30 seconds. So 30 seconds is half a minute, right? 0.5 minutes. Right. And basically the question wants to calculate the probability that we detect the particle in the next 30 seconds. So that means that P of x less than 0.5. So here we use the CDF. We don't have to use the CDF. We can integrate the PDF. So this is equal to integral from 0 to 0.5 lambda e to the minus lambda x d of x, right? And remember that was equal to e to the minus lambda times a, which is 0, minus e to the minus lambda times b, which is 0.5. Right? And that is equal to, sorry, So this is 1. And this is, my lambda is 1 over 0.5. So e to the minus 0.5 divided by 1.4, right? This is my lambda. And this is 0.3. Any questions so far? Okay. Or as you can see here, I can say that probability of x less than or equal to any number is equal to f of x, right? And f here is the CDF. This is the definition of the CDF. I don't know if the CDF is provided in the crib sheet or not, right? But if it's not, it's easy to, we can quickly calculate the CDF of the exponential distribution. So f of x is integral from 0 to x of lambda e to the minus lambda x d of x, right? This is the definition of f of x, right? Capital F of x is the integral of small f of x from 0 to x, right? And now this is e to the minus lambda times 0 minus e to the minus lambda times x. And the first term is 1, right? So it's 1 minus e to the minus lambda x, right? So this is the equation for f of x. And this is where this is coming from, right? So for example, f of, so f of x, f of any x is 1 minus e to the minus lambda x, right? So x can be any number. Here I plugged in 0.5. Any questions? So this part had nothing to do with memoryless property, right? It's a normal question that we did before. Okay. So now I calculated the probability that, a particle is detected in the next 30 seconds. Now let's assume that, we know that in, 5 minutes, no particle has been detected, right? So for 5 minutes, no particle has been detected. What's the probability that there is a particle detected between 5 minutes and 5.5 minutes, right? That probability is still 0.3, right? So the fact that no particle was detected for 5 minutes doesn't increase the chance of some particle being detected in the next 30 seconds, right? So if we didn't know that exponential distribution is memoryless, so let's actually see the question. So the next part says no particle has been detected in 3 minutes, right? Will the probability that of seeing a particle in the next 30 seconds increase because the particle is due, And the answer is no. The probability will not increase. It will remain 0.3 because exponential is memoryless, right? If we didn't know exponential is memoryless, then we had to compute this conditional probability, which is a pain, right? Because to calculate this, this is not out of the scope of this course. We know all the tools to calculate this, right? So basically to calculate this, I have to write, this is equal to the intersection, right? It's a conditional probability. We know how to calculate conditional probabilities, right? It's probability that x is between 3 and 3.5 divided by probability that x is more than 3, right? And now I can compute all of these terms, right? But compare this, to the solution here. This is much more, involved than this one. Right? So we can simply say, no, the probability is the same. It's still 0.3 because exponential distribution is memoryless, right? And this is the same thing that I mentioned in the previous class. If you buy, a new RAM, or if you buy a RAM that has been used for 1 year, the probability of each one failing is the same, right? Because rams, you know, don't tear down. They're not subject to wear and tear, right? So, and this may sound strange because, you know, if you buy a used, you know, tire, the probability of that tire failing is higher than if you buy a new tire, right? Because tires, you know, are subject to wear and tear, right? Or if you have like a shaft rotating constantly, you have fatigue in this shaft, right? So it gets old and old, and as it ages, the probability of failing is higher, right? So those are not exponential distributions. If something is exponential, it's memoryless. It means that it doesn't age.
What other physical phenomena follow the exponential distribution?
I guess characters from Marvel stories that don't age. Anything that doesn't age is exponential, right? Anything that's memoryless. I don't know. That's a very good question. Other than RAMs, you know, I don't know anything that doesn't age. And probably CPUs as well. CPUs don't age either, right? So you compute, you know, you give jobs to CPU to compute. It doesn't age. Probably GPUs as well, yeah. So I mean, some things do wear, right? So for example, in GPUs, there are some parts that act as heat sink, you know, because you don't want them to heat up, right? And those are like glues and stuff like that. So those are like mechanical parts. So they do, you know, so basically your GPU gets hotter and hotter, right? But the actual electronic part, it doesn't wear and tear, right? So it's memoryless. So any intuition why exponential is memoryless? This sounds very counterintuitive, right? Where does this come from? So we have not covered this in this course, right? But they basically, I posted like a PDF on Moodle for people who are interested to see where Poisson distribution comes from, right? But Poisson distribution comes from binomial distribution, right? So from binomial, you can prove Poisson distribution, right? In binomial distribution, when n goes to infinity, n is the number of experiments. Then the binomial becomes Poisson, right? And remember, in binomial experiment, the events are independent from each other, right? So this memoryless problem, this memoryless property, it comes from the independence of events, right? So the fact that you flip the, you know, a coin 10 times and you always got head, it doesn't change the probability of the next flip, you know? So the root of all of this, you know, strange property is independence. Okay. Yeah, so in this case, I like the solution here. So you see that we didn't use the memoryless property. We actually calculated all of these numbers. And the answer that you get at the end is exactly the same, right? But you didn't need to. You could just say that, oh, this is memoryless, so it's the same answer as before. Okay, so that's the end of chapter 4. So let's do a couple of exercises where, you know, I think are the tricky, you know, suggested problems in the book. So the first one is this one. We have an assembly that contains, so this will be, I think it's already 11:16. So this will be the last question that we do today, and then we do the rest of them on Friday. So we have an assembly that contains 48 blades. 5 blades are selected each day. If a dull blade is selected, the assembly will be replaced. Okay. If 10 blades are dull, what's the probability that the assembly is replaced in day 1? Okay, so we have an assembly that has 38 not dull blades, D prime, and 10 dull blades, right? And 10 blades are, oh, sorry. 5 blades are selected, sorry. So we select 5 blades. And we want to calculate the probability that so the question is, if a dull blade is selected, the assembly will be replaced. So here we probably want to calculate the probability that we have at least one dull blade, right? Among 5, right? So once I do encourage you to summarize the question into statements like this so that you exactly can, you know, pinpoint what the question wants. The question wants the probability of having at least one dull blade among the 5 dull blade among the 5 blades that we select. Any questions so far? So here, are we selecting with replacement or without replacement? Without, right? The question doesn't say, but it's clear, right? If you're testing for something, you're not going to put it back and test it again, right? So it's obviously without replacement. Right? So so it's without replacement, and now so whenever you see at least one, you know, it's easier to calculate the complement, right? So that's going to be equal to, so I'm going to write up here, that's going to be equal to P of, 1 minus P of 0 dull blade. Right? And now it's much easier, right? So I'm selecting 5 blades. I want to calculate the probability that none of them is among the 10. So that's going to be 1 minus, so I want all of these 5 basically to be from the 38, right? So 38, choose 5, divided by 48, choose 5. So that's the answer. Right. So I didn't write one part of it. It's multiplied by 10, choose 0, right? But that's 0, right? Sorry, that's 1. So that's why I didn't write it. So here I'm using, I think it was called hypergeometric. You don't really need hypergeometric because, you know, I'm selecting 5 out of 38, right? So it's a counting technique. So I intentionally asked the at Concordia to create noise to wake you guys up. And I think it's working. Okay, so yeah, that's the final answer. So that's the answer to part A. Any questions about part A?
For questions like this, you also ask us to give a decimal answer, right? Because I state that often in your sample.
What is it? Sorry?
Often in your sample questions, you state that give me a decimal answer.
Yeah.
Something like this also
Those are not sample questions. Those are in exam because it makes it easy for me to grade, right? I do look at, you know, I don't look at the final answer only. If the final answer is correct, then my job is super easy. You get the full mark. But if your final answer is incorrect, then I will have to go and look at what you did, right? And that's why I always ask you to give me a decimal, you know, answer, because it makes grading very easy because most of you get the final answer right. So I don't have to go and find out what you did. Right? And there's often multiple solutions to the same question, right? You saw that, you've seen that so far, you know, like one question can be solved, you know, using 2-3 different solutions, right? Okay.
So even for your hypergeometric like that,
No, this you can plug into your calculator. So these are not huge numbers. You can calculate this one. Yeah, you're not going to multiply 38 by 35, you know. Does the ENCS approved calculators have a factorial? Yeah, so. Yeah, okay, so there you go. Okay, so the next parts are a bit trickier. So if 10 blades are dull, what's the probability that the assembly is not replaced until day 3? So I mean, this one you have to really think. So basically it says that is not replaced until day 3. So that means that it's not replaced in day 1, not replaced in day 2, replaced in day 3, right? So here it's like a combination of 2 things, right? So you have to separate into 3 days, right? So I'm going to answer part B in purple color. So this is day 1, day 2, day 3, not replaced, not replaced, replaced, right? So, and different days are independent, so I have to multiply these probabilities by each other to find the solution to part B. Right? So what's the probability of not replaced? We already calculated it. The probability of not being replaced, so P of R prime is equal to P of $0. And this is
But for the second day, isn't it different since you?
yeah, that's an excellent question. So let's write it down first.
I think it's not different because it's 48 new days every day. Is it? Yeah.
Yeah,
It's in assembly, so it takes 48 new days every day. So it doesn't matter.
exactly. So yeah. So in day 1, this was basically the probability, right? So 38 choose 5 divided by 48 choose 5, right? So you're right. If you read the full question, it says that the blades, the entire assembly is replaced every day, right? So the next day again is an independent event, right? So we are looking at a new day, you know, everything is new. So again, probability of R prime in the second day is the same answer. Yeah. If they are dull. But anyways, you know, so this is the part that the question gets, you know, a bit ambiguous, right? So we have to know in day 2, are we going to remember which blades we tested? I don't think we're going to remember which blade we tested, because even if we tested a blade and it was a good blade, it might be dull today, right? So it doesn't mean that if we tested a blade yesterday, I'm not going to test it again, because yeah, it was good yesterday, but today it might be dull, right? So this is where you have to, you know, use your common sense to find out that in the next day, am I going to check new blades, or I can check the same blades as before, right? And I think, you know, we should check the same blades as before, because blades actually do get dull with time, right?
So I'll raise my hand.
No, so in the exam, again, you have to use common sense, right? So whatever, you know, there's like multiple interpretations, you have to use common sense to see, you know, and then, you know, I'm a fair grader. If I actually do see that, yeah, your common sense does actually make sense, then you will get the mark. Yeah.
So like, for example, in this question, it can be also interpreted that, for example, it's a manufacturing company and they're shipping out blades, and if they pick 5 blades, they make 48 blades every day, and they pick 5 for quality assurance. And if they pick 5 and one of them is dull, then they cancel this shipping. So every day is a new set of 48 blades, right?
Yeah.
So this makes sense also.
Yeah.
It can be both, right?
Yeah.
So
yeah, that I think that's a better interpretation. Yeah. So this is the company that makes, you know, these assemblies. They have 48 blades. If they check them, they check 5 of them to make sure, you know, it's okay. If it's okay, it basically sends it out for sale, right? And then next day is a new assembly, right? So it's always, so these are, so basically what I wrote here is correct. We have to multiply these guys. They are independent. Yeah.
Modeling as geometric distribution, I consider the first success is x equals to 0.
Yeah, this is, yeah, exactly. So what I wrote here, this is exactly geometric. Failure, failure, success. Yeah. Yeah, so the rest of part B is straightforward. Right. Any questions so far? So let's then do part C in the next class on Friday.
Sure.
Yeah, go ahead. Let me first stop recording and then